Anyway, I thank the organizers for giving me the opportunity to give this talk. But after a great talk by Chris, okay, I mean, who has really looked forward, I'm trying to look back, okay, and try to see, okay, I mean, what we have learned over the past, and can our past can drive us, okay, to move forward. So I'm a little bit sorry for the way I'm trying to do that. Well, I think when we started doing experiments in high energy physics, we did not really bother about anything, okay, I mean, because we are looking at not what you call rare processes. We are looking for processes which were quite abundant. And we are really looking at optical techniques, okay, for looking at things. So natural intelligence was sufficient to identify particles and relied on computers only to take care of some numerical computation for the measurement of particle momenta. So that was all about it. So this procedure was good enough for an understanding for not so rare processes which are produced in the nature. But as knowledge progressed, we had to go to high energy experiments through collisions for moving particles. So we moved from fixed target experiments to colliders like ISR or Adone. And we looked for rare processes. So we did not look at cross sections at the level of milliburn. We were looking at microburn, nanoburn, picoburn, femtoburn, and then maybe going to autoburn in the future. So the detection techniques also changed with newer and newer technologies. And then we have a complete detector systems which are built by combining detectors of different technologies. So to combine these, experiments are no longer done by a group of human beings in single digits. It moved to 2 digits, 3 digits, 4 digits, and I do not know what is going in future. It may be going to 5 digits. And even the natural intelligence was not sufficient to understand what the new detector systems will provide. So obviously we are going from machine learning and all that, but we also need something, okay, where we utilize our present knowledge that model detectors in the computer and try to simulate what particles from an interaction will give signals in this detector system. And that is what detector simulation does. So the first step in this detector simulation code try to simulate showers which are created by electrons and photons, and then hadrons and nuclei. And these are the so-called old transport code. One of the first transport codes which came, okay, the well-known EGS code, which was developed at SLAC during the late 70s and early 80s. And obviously, even prior to that, okay, I mean, thanks to the building of the nuclear reactors, there existed codes for transporting neutrons, essentially even the thermal neutrons, okay, through the material. So the neutron transport code, okay, was extended to higher energies, which became the so-called HETC code, the high energy transport code, which is built at Oak Ridge National Laboratory. And there was also a parametric approach for this came as a form of a Kaisha code, which is developed to satisfy the experiments at Petra. So the characteristics of this course was that they have a fairly good description of the detector physics through the current understanding at that time of the strong electromagnetic and weak interactions. But the propagation of particles to the various components of the detector was entirely left to the ingenuity of the experimenters who were building the detectors and using these cores. So CERN was considering building LEP at that time, and some of the CERN scientists thought of launching a software package which handles both of this, the detector physics part, as well as propagation of particles in the presence of electromagnetic field. And that was the first tool which was built, which is called GEON3, which can handle both of them. So during the 90s, the experimental high energy physics also realized that they were using software tools which are very much outdated by the industry, and future extensions of using that computing language, Fortran, would be very, very difficult. So CERN at the time was also thinking of building the Large Hadron Collider with a plan of using them for the next 40, 50 years. So they have to form something to move forward, okay, from what they had in the form of geometry to something which was a little bit modern at that time, okay? I mean, obviously in the 90s. They may not be modern anymore. And so they have to move to implement the simulation software in the newly adopted language, which is C++, and a technology which is object-oriented programming. They chose C++ because they needed something which is has been used in the industry at that time and also can work rather fast. And so it has to be something which is compilable. And that was the really thing, okay, we moved from the GN3 to GN4. There are few other software toolkits which are used in this field, MARS, FLUCA, and MCNP. The MARS is used for accelerator and beamline designs. FLUCA is used for accelerators, beamline designs, as well as radiation tolerance studies in detectors. And MCNP is one of the oldest course which has been developed over years. Okay, it has started from the 40s and all the way that has been developed for the last 80 years and is widely used in nuclear physics applications. I'm not going to talk about that. I'll only talk in the context for what we apply, okay, in standard experiences, that is physics Gen4. So what we have a physics generators which provides us with the particle 4 vectors which are fed to something where the experiments have to provide the description of the detector through some of the tools available in Gen4. And with these tools, okay, I mean, they are propagated and they generate the so-called hits in the sensitive part of the detectors. We add to that something which comes from the other interactions, which is called pileup. Add noise to that, we simulate the electronics, and then we simulate the raw data. And once we have done that, okay, and if we analyze those raw data, we will be able to understand the various efficiencies of this detector, the backgrounds, and determine the systematic uncertainties. So this is the main tool, okay, for doing all that. But also it is used, and is very, very important, that is used to decide how the detector should be built. So this has got mainly two purposes for in a high energy physics experiment. And I think it's not just high energy physics experiment. I think GN4 tool is now also utilized, okay, I'll come to that, okay, I mean, for other things. So now the predictions of this depends on two things, okay, how good the physics generators has predict the physics, real physics process, and how well you can describe realistically the properties of your detector. So these are the two important things for doing that. Now, I'll come to the history of GN4. During 1993, okay, I mean, a mini workshop was held with the participation of scientists from two laboratories, KEK and CERN, to look into the possibility of making an object-oriented version of GN. And they came up with a proposal consisting of 29 people from 19 institutes from nine different countries. The proposal was approved and the GN4 collaboration was formed as a CERN project, which is the so-called RD44 project. Now, whenever we have something which is called object-oriented version, it comes through 4 phases. It requires a requirement document. It requires the so-called analysis, design, and finally implementation. Now, as far as the requirement documents is concerned, obviously we already had a history of from LEP. So we get the experience from GN3 and other simulation programs which existed at the time. So this usage was extended to the application now to space science and medical physics. So even in the formation of requirement documents, we already included the usage in other applications outside nuclear high energy physics. Now, once we have done that, then we have to utilize some of the object-oriented tools, okay, for doing that. So he adopted what you call the unified modeling language, which is adopted from a Bush methodology. And then utilizing that, we made the object diagrams and defined the so-called analysis stage. And from that, we said, okay, all the closely coupled classes which are formed from that were clustered together to form the class categories. So the whole project was divided into categories. And from that categories, we started trying to build up design the GN4. And by 1996, the design work was complete and the prototyping was started. So this is some sort of a diagram of the categories which you have. We started at the level which is something which is called global, from which for example, where you define the 4 vectors and things like that. And then we slowly build up, we come in from material, geometry, tracks, heats and digitization, and all the way up to the giant level. Okay, so there are 17 categories all the way up to here. And the main thing is that if you look at the way the dependencies are, dependencies are only one-sided. So once you have done, for example, tracking, okay, I mean, you don't really, I mean, the event does not really have to bother anything about anything else except tracking. So it is easy, okay, to have several people. I think this is a system which is built not by only 3 or 4 people. I think the GN3 was built essentially by 5 people, and GN4 was built by 100 people. And when you are building a system of 100 by more than 3-digit number, you have to decouple break up the system into independent parts. So I marked it, this one, the digits and hits, because in the discussions of the analysis and design, so I mean, there are 3 of us from the XL3 were involved. Okay? I mean, my boss, Francis, me, and a young boy, okay, for Stefan Piperov, who had did the analysis and designs for the digits and hits. So the alpha, after the things was done, the alpha version of GN4 was released in April 1997. We satisfied the comparable functionality of GN3 for whatever GN3 could do. Okay, the geometry, tracking, electromagnetic physics, high and medium energy hadronic physics. It is easily exchangeable physics models to satisfy the experimental condition. And the weakness of this particular alpha version was the persistency. That means, okay, you have to, whenever you generate hits and all that, you have to provide those things, okay, to the reconstruction program, and that is not done so well. The object persistency was done through an object database system, which was advertised in a separate R&D project, RT45 or CERN, which did not really provide a good enough persistency platform. So after that, the next version came, the so-called beta version, which was released in July 1998. And the major experiments at the time were invited to test the code through an application software specific to the experiment. It really now has a computer system with documentation, examples, and tutorials. And obviously, they try to provide the replace this ODBS by a root software, okay, for doing the persistency. And they extended the geometry code to directly couple to the CAD models, so that, okay, the engineers, whenever they give him a model, okay, they can be directly integrated to that. So once the beta version was delivered, this signaled the end of the R&D phase. The project RT4040 was closed, and the first production release of GN4 was available to the collaboration in December 1998. Now, the electromagnetic physics was described in great detail and validated using the predictions from the EGS4 shower code, which is the so-called gold standard in all simulation toolkits. but it was extended at very low energies, below 10 keV, because it really has to work for experiments with optical photons and things like that. Okay, so you really try to extend to come in whatever available in EGS code, and that was done, introduced from the first principle. So this was relatively easily taken care of. The story is totally different for hadronic physics. We do not find any single model which could explain the hadronic physics from the lowest energies to the highest energies, even from 10 keV to the 100 TeV. And you really want to go down to about a keV level, okay, I mean, particularly, or even lower, okay, to look at the neutron interactions. So the Janford team has taken the approach of using several models which provide the predictions close to the data in different energy domains and combine them in one list, which they call physics list. You have one model for one type of particle, and then you have another model for the same particle, and then you go to another model, and then you can combine all of them together. And this is just one particular physics list. We have multiple physics lists, which is there in GN4. Now, once you have a physics model, you have to say, okay, this physics model is good. The only way we can say a physics model is good, okay, it can explain the data fairly well. And this has gone through an extended validation thing, and there are two types of validation which is done. One against the so-called thin target data, which means that the experiments which has published the data after making all the detector level corrections. So the comparisons against this data do not require predictions from other models other than the model which you want to validate. So this is one data set of data which is coming from a Brookhaven experiment done with a proton beam at 14 GeV on this one is essentially on beryllium and gold target, and at various different what you call transverse mass at different rapidity regions. So it's a double differential cross sections, and you can see the predictions of 3 different models against that. And there's the one in the magenta, which is in between. Okay, there's a model where the predictions are not too bad. And that is the one which has been adapted, okay, for in this particular energy region. This is what you call the so-called Fritjof model for doing that. So this is one type of thing. Okay, and the other thing is against calorimeter data. So these data are experiment specific. So Janford delegated this task to the experiments themselves. Okay, and here is a comparison of CMS data where they have measured the energy response as a function of momentum of the track, where the calorimetric energy is measured, okay, and compared with the track momentum. And this thing is that, okay, I mean, you can see that over years, the predictions of one type of physics list has done a fairly good agreement with the data. Now, that's as far as the GN4 part is concerned. So we have to apply that to a given experiment, like a LHC experiment. I have chosen the experiment where I'm most familiar with. This is the CMS experiment. The main thing about this experiment is that it has consist of, as Chris has pointed out, it has got various different detector components. And every detector component has its own simulation requirements. So the idea is that, okay, when you have to make a simulation which is a region-based optimization. So that is what is done in designing this thing. Now, CMS formally started as a collaboration in early 1990s with the Avian meeting. And the management team at that time knew the importance of simulation, and they started the effort immediately, which is led by a Finnish group. And soon other groups joined this activity and made the first version of a tool which is called CMSIM1, which is based on GN3, because there is no GN4 which existed at the time. And the important thing is that there was early collaborators from in this particular thing came from this Aleph, and they chose a memory management package called BOSS. So when some US groups joined this effort, there was a real fight which began, mainly because, okay, I mean, Geometry uses Fortran with one memory management package, and then this thing now requires two memory management packages. So, and when the US group says, okay, look, it is better to have only one memory management package, either rewrite Geant with BOSS or use Zebra, okay, I mean, as the real memory management package. So this the software management team, they delegated this decision to a task force, and there was a meeting in the UC Davis, and there it was a decision was taken to use Zebra and not to rewrite Geant3. So we have a CMS simulation detection package which was started, which was Geant3 based and written in Fortran 77, and we had detector experts from every major detector who wrote the geometry of the CMS detector. The CMC was a tool not just for detector simulation, it was also for reconstruction. And when we had a C++ with that, okay, I mean, the reconstruction code for part of the detector, particularly for eCal, was written in C++, and CMC was not a pure Fortran product, it became a hybrid system. Now, this was used in writing the technical proposals of CMS, as well as writing the technical design reports from the major detector components. And we learned quite a lot from CMC as far as the description of the detectors are concerned, and we translate that in for our future. Now, I jumped a bit. Yeah. Now, one important thing when you do an experiment is that we try to understand the working of individual detector. So test beam is an important tool for doing that. So during the 90s, we had a test beam with a so-called hanging tile, which are alternating layers of absorbers and scintillators in a magnetic field. And one of the things which we learned that the orientation of the magnetic field and the particle direction is important. If the direction of the magnetic field and the particle directions are same, then we have the scintillar brightness is the thing which happens. But if they're perpendicular to each other, we have a combination of the scintillation brightness as well as the increased path length. And this is what we have in our CMS detector. In the first one is the N-cap detector, where the magnetic field and the direction of the particle are parallel, and in the barrel detector where they are perpendicular. So this is one of the things which we learned from this, and this we really see in our detector simulation. So we had a first standalone simulation code which is written in Geant3, and then we translated that in Geant4, and we contributed from CMS as an advanced example to Geant4. Okay, that was the first contribution from CMS to Geant4, which is called the so-called composite calorimeter example. So as the knowledge of the future tracker grew, we had a concrete proposal of the tracker geometry, which was required. And this was written in a way, okay, we start with the components which are described in detail, like the silicon wafers, the readout chip, the pitch adapters, base plates, supporting rods, cables, everything, the entire system of the tracker which is written. These components are then combined to make the so-called rods, petals, complete subdetectors, and finally the tracker. The goodness of this was really demonstrated. I'll only say the goodness and not the badness of the simulation code. The goodness of this thing is that when you looked at the first check the weight of the components, we measured the weight of individual components, and we found out that we described all the components rather well. And we took the weight of the entire tracker when it was first constructed and transported in the 0.5, and we looked at the weight in the simulation, and it's found out that also comparison also gives a near perfect agreement. The second comparison was done from a study of the conversion vertices of the photons and nuclear interactions. So where you have preferential conversions will happen where you have the heavy materials. And that's exactly, I mean, you have these comparisons over here, and you can see that the data and Monte Carlo agree rather well. And that is where the various detector components are. So this is an interesting thing which is observed. So once that was so far the geometry part is concerned. So once the beta version of the UN4 was available, CMS used this and made the first prototype software, which is called Oscar. I think the O stands for object-oriented. I don't know. S stands for most likely simulation. Anyway, I don't know the full expansion of that. So the first, we had a version where we only tried to test the simulation code with UN4, and it had no connection with the reconstruction code. Then we have a combined version where we're using a common tools for the simulation and reconstruction came in the form of a Cobra. This is basically work of our colleague from Vincenzo Innocente. And then we have Oscar and Orca. And that was a complete, the first simulation. And of course, the Orca was used for the physics TDR of CMS. Now, here is some comparison which came from the two versions of the Oscar. You can see the two versions of Oscar agree pretty well. Now, as I said, the late arrival of the reconstruction code for the physics TDR prompted an in-depth review of the CMS software. And there was a severe criticism was done on the CMS software at the time, mainly on the usage of the persistency. So we had a new event data model, which was proposed by the Formulab team, which was adapted, and the first version of the CMS software was released. And the simulation code obviously was revised all over again, and we rewrote the simulation tool for CMS at that time. And a special tool was built using the XML language to facilitate the geometry description. And this approach was later taken up by the GN4 team. So the first version of the XML part came from CMS. For a brief period of time, we had a presence of two GN4 experts in CMS. And that really helped us to really make a good enough CMS software. And the code was really optimized to consume less CPU time and memory. And our benchmark is that we have a CMS software, simulation software, which is 8 times faster than the Atlas full simulation code. So that is one success story of CMS. And we obviously utilized the test beam data also to help our simulation code quite a lot. And not only that, also this also helped in developing the so-called physics list of GN4. In 2006, CMS has a test beam with a prototype detector for the hadron calorimeters. This is the barrel one. This is the NCAP one. We had a real ECAL, and we had a special beam line which could produce beams, the hadron beams from 2 GeV to 30 GeV pion beams. It's not just proton beams. I mean, pions have a finite lifetime. So having a 2 GeV pion beams coming in, you cannot really start from a beam 200 meters away from that. So they made a special beam line for doing that. And after having that beam, they measured the response of the detector from that and try to compare that with the Monte Carlo. So we developed our simulation software was really try to describe the test beam setup as well. And we utilized that, and we tried to compare that with the physics list which existed at that time, which used to be a fully parameterized physics list or something which is starts from a quark-gluon string model and which has a better theoretical insight. And neither of them really describe the data. You can see the data is black over here, and the red point is the parametric one, and the blue is the so-called QGSP one. So the two things we learned, that we ignored the what you call the effect of saturation of producing scintillation light. Whenever there is an scintillation light is produced, okay, I mean, and if there's too much of light is produced, that is an it is somehow it has to be shrunk, okay, by, and there is this so-called Box correction is there, and it is true for both for crystals as well as for the plastic components. And there was some sort of a difficulty in convincing our IISc colleagues, okay, that who are really intense in making a very high precision electromagnetic calorimeter, but they have to also have to, as Chris pointed out, okay, I mean, they have to deal not just for the electromagnetic calorimeter, also for the hadrons. So eventually, okay, this was the Box law was introduced, and we had a slightly modified physics list, and obviously you can see at the very end, okay, we had a fairly good agreement between data and Monte Carlo. So this is the first thing, is that the LHAP could explain the data, and for QGSP we have to introduce QGSP with this is the QGSP and with a Bartini. QGSP model alone cannot describe the data per se. So that model not only could describe the total energy measurement, that also could describe the shower profile. This is the longitudinal shower profile, which is measured by the test beam. This is the lateral shower profile, and all of them can be measured pretty well. The only thing which was seen in the test beam and which were ignored, okay, 5 minutes, okay, which were ignored was that we have some spurious events, okay, where you have very large energy deposits over here, and which could not be explained by anything else. So once it is ignored, okay, I mean, obviously we cannot ignore for a long time. So as soon as we have the real data coming in, we saw two things. We saw that we have a very large energy tail, okay, in the ECAL barrel. We also saw a large tail in the missing ET. We had to have a good measurements of the energy. We have to have a good measurement of missing ET, and obviously there's something which is missing. So what is missing? There was a ECAL is read out using the two types of detectors, one in the barrel and one in the end cap. The one in the barrel was APDs and the one in the end cap was VPDs, and they're used slightly different ways. Now, the APDs has got two thin layers of silicon, and what happened in that, okay, that once we try to simulate the APDs separately, we found out we could explain the energy response in the APDs as well as the timing in that thing pretty well. So this is what you call, okay, the first failure because of our lack of understanding of the detector, and the success of the simulation mainly because once we understood how a detector should work, okay, I mean, we can explain our detector through the simulation pretty well. Similar story is from the tail, okay, for the thing, for the large tail in the what you call the missing ET, and that is mainly because again the test beam saw this thing and we missed it out. At the end of the forward hadron, the so-called forward calorimeter, with the energy, the Cherenkov light is read out by photomultiplier tubes, which is coming at the very end. And this, if some of the things comes directly and hits the photomultiplier tubes, it just lights up and gives signals. So once we could really model the fibers and the photomultiplier tubes, we could really explain those parts of the data as well. Now, nothing is, once you have a static detector, you can see, okay, I mean, it is almost a dead detector. Unfortunately, okay, CMS is not a static detector. It has been changing all over the time. So the simulation program also cannot be a static object. Okay, it has been developed all over the time, and it is trying to keep up with the things with from the LS1 to LS2 to LS3, and maybe with after LS4. Now, so this is the thing which is coming from LS4. We have a new tracker. We have the barrel calorimeters are changed for both ECAL and HCAL, but we have a very good, better timing resolution. We have layers of detectors for the to provide good timing information. The muon detectors will provide a better solid angle coverage, and the NCAP calorimeter will have this, the so-called high granularity calorimeter. So all these things are now introduced. This was only the part which goes in the CMS detector, but we also are not static in the GN4 as well. One of the first things which we try to do, we try to vectorize the GN4, and we hope that we can improve the timing, CPU timing by a factor of 10. Unfortunately, by vectorization did not help it. But the only thing we learned that we could get up by a factor of 2. And this is identified due to a better algorithm and proper packaging of the code. So this experience was transmitted to GN4, and all this particular thing has happened is that the so-called vectorization thing gave us only a publication called GNV publication. Now we utilize this thing in GN4, and CMS was one of the first experiment, okay, to utilize some of these components, which is the vectorized version of the geometry. Which has been fully integrated in GN4, and it showed a significant improvement in performance of the CMS simulation. We do not get a factor of 2, but we get a 10 to 15% improvement in speed. And we also checked the physics quality, and we saw for both tracking and calorimetry, the physics qualities are as good. So we come to my last word. Detector simulation has been living with the high energy physics community for the past several decades. The general toolkits originally designed for high energy and nuclear physics find their utilities in space science, medical physics as well. I must admit, okay, the paper I have my highest, what you call citation, is the GN4 paper, and the GN4 paper has the maximum citation from medical physics. It has got more than 1,000. I think it's now have maybe 1,000. I think it's maybe some 10 years ago. It might not have now a couple of thousand citations, okay, coming from medical physics essentially. The high energy physics experiments use these tools to design the experiments, to understand the anomalies observed in the experiments, and obviously to interpret the data, to test the physics models, finding evidence of new physics, discovering particles yet unseen, and completing all measurements by helping estimation of the uncertainties. The field of computation is changing with time, so we need new ideas both in hardware and software, and that is which you're getting. Okay, so we're now trying to utilizing GPUs and FPGAs on the hardware side and use artificial intelligence on the software side. So the tools as well as application software have to keep up with the technological advances. Thank you.
Thank you, Sunanda, for this nice talk. Any questions, comments, Chris?
Sort of as a testament for how important GN4 was for the collider community, I believe when you said that, the Atlas and CMS were tasked with, sort of validating it against their detectors. I think 20 years ago, the person in charge of that is now the Director General of the laboratory, right?
Any other question, comment?
Giant4 is used also. I mean, I've seen colleagues working on the laser plasma acceleration to analyze their data also. So when was it, when it was written, was that also an intended application, or that has just come as a byproduct?
Now, as I said, okay, it is really written as a general tool of for basically studying the interactions going from EV to TeV range, several hundreds of TeV range. That was the thing why it was the way it was written. So it came in the requirement document for that.
Okay.
Now the applications of those came naturally, okay, from the people who are interested in this. They have special workshops, okay, for definitely coming from space physics and medical physics, this I know. Obviously, it comes from particle physics and particle physics community, I say. Outside that, I really do not know.
Okay, John has a question.
Well, it's not actually a question, it's a piece of information. So I just checked on Inspire, which doesn't maybe cover all the possible citations of GL4. But the GL4 simulation toolkit paper has 16,155 citations.
Very impressive.
Well,
Yeah.
that's good news.
I have a comment. Yeah, so you mentioned AI. So is there an aspiration, or is it already being implemented? I mean, what do you mean by it?
No. The thing is, the Gen4 is now moving also not for just full simulation, also for fast simulation.
All right.
So when it goes for fast simulation, obviously, okay, I mean, they try to utilize all the tools which is available from artificial intelligence into this thing. So this is an area where it is moving in future. Yeah.
Okay.
Anybody else have any comment or question? If not, let's thank Sunanda once again. And I think let's thank all the three speakers in this second half of today's session. Thank you very much.